Hi. Recently Amir stopped by and we had a coffee and a good chat, and he brought me an LED display. He says he has one at home as well, the same, but with some scratches, and yeah, so I thought, I said I would reverse engineer it for him and figure out how to drive it. So I thought, rather than just do that, why don't I make a tutorial and do it on camera so other people know how to do it. Now this is a double-sided board, so it should be kind of straightforward. It uses a lot of off-the-shelf chips. I did have a look and found the data sheets for them all. Those yellow ones are actually resistor arrays. So, but yeah, I will hopefully provide the links to the data sheets for this, and a finished schematic should be available in the description. Though I haven't reverse engineered it yet because I'm just doing the intro. But yeah, I will take you through step by step how to do this, and hopefully we'll have some nice success and just hook it up to an Arduino or a PIC at the end and do some basic code. Okay, so on to the next bit. Okay, in order to reverse engineer this, we need to print off some pinouts. I've basically done all this. I will provide a link so you can download this from my website. Basically, that is the flip-flop, the LM74374 flip-flop. It's an octal D-type flip-flop. So basically, it's acting as an on-off switch between the input and the output, logic level. And then we have the UDN2580, which is an 8-channel source driver. And then we also have the DS2003, which is a high current / voltage Darlington driver. And then we have the screen, which is the LTP2157AG from Light On. And there's the map of the pins as looking through the top. So we're going to use this to determine the pinout of this. Now, if we flip it over and have a look, you can see the screen is actually handled in groups of 3, at least as far as all these chips are concerned. So, and if you look at the chips at the top, they're in 4 groups, and there's 12 displays. So, I reckon it's 4 sets of 3 displays in combination. So, without further ado, let's beep this out and have a look. So you'll need a test meter, preferably with a beep setting on it, so that way you can put it outside and just hear it. And it's a cheapy $30 one from eBay, but it does okay. It's not the greatest. So make sure you're right on here. So basically, we're gonna have a look. See, from the looks of it, it all runs through this resistor array, which I believe they're all connected to there. I'm going to double check that. That goes to the UL. Having a bad day. Okay. That is, yeah, an UDN 2580, and then that connects directly to the 374. So my theory is it goes through that and then drives through that to the screens. Alright, so let's just see. So you can't see the traces on the other side or this side for these, so I'm assuming they're the ones that are going between the chips. So let's have a look. Yep, they all connect. And let's see. And obviously they're connecting to there, so this goes to the inputs, and then comes to the outputs, so that way. So let's figure out where it all connects. So now let's just see, is that going to be, oh yeah, it's low enough resistance to beep, which is 220 ohms. Yeah, 220G. It says on the display that it's 220 ohms, isn't it? Oh yeah. Oh, it's 22 ohms. What the hell am I doing? Eee. Too much coffee or not enough coffee. Either way, causes the same effect. Okay. Now, I want to check to see if, because it looks like these are actually in parallel. 1, 2, 3, 4, 5, 6, 7. Looks like 7 pins are paralleled up. One here. One. No, it's a 7. It's a 5 by 7. So my guess would be this is the row driver of the circuit, but well, we shall see. So let's go for this pin. Oops, sorry. This pin is pin 18. That goes to there. So that's pin 9. Pin 9 is row 1. Row 1. Okay, so here. So I have to push them. Oh, there we go. I have to push them slowly because this is not the quickest at latching. So that was pin 12. With 8 and 12, I can't count, that's 14. Pin 14, row 2. Well, I shouldn't even look at that. Okay, and this one goes to, let's just goes to that one, which should be pin 7. 7, row 6. I thought they were going to be in order, but oh well. Okay, 13 slash 12, which is 4, row 4. Row 4, which should also be pin 5, 1, 2, 3, 4, 5. Yeah, see, they're internally connected. Okay, now this one, which is pin 1, row 5. And that one, pin 7, which is row 6. I'll make a boo-boo here somewhere. Alright, row 6 has been 16, 1, 2, 3. That's pin 8. Pin 8 is row 3. Wait. 1, 2, 3, 4, 5, 6, 7. So that's 7, 8. 8. Go 3. Okay. definitely the caffeine. Okay, it's going in order actually, which is good. Okay, so third from the end. And that one is pin 2. Pin 2 is row 7. There we have it. Those are the row driving pins. Right, nicely all in order. Okay, so we can then translate these over. So that, oops, sorry, I was short now. This here is the event of this one, so 1 is row 1. You can see that goes over to there, which is, okay, so that's pin 1. So it's 20, 19. 19. So it's 1. Okay, and it goes there. 20, 19, 18, 17, 16. 16. Okay, I don't know why it keeps doing that. Okay, so, okay, yeah, we got row 2 is on 16, so the row 3 is on 15. Row 4, and that is 12. Row 5 is 9. Row 6 is 1, 2, 3, 4, 5, 6. 6 is pin 6. Row 7 is pin 5. And this output, I don't know, where does this one go? Does it go anywhere? Curious. Let's see if it goes somewhere. Now, I usually accomplish this by using a flashlight. It takes forever to turn on, strangely enough. Right. Sometimes you can get it in there and see a shadow of a pin. I can't see anything of where it's going, so it may not even go anywhere. I don't know why they would add that. So yeah, so these would be the outputs. So these are the inputs that drive through it. Okay, so that's all of those. Now, so those go here now. My question is, where do they go from there? Logic would state that they go to a header somewhere. So row 1, so pin 18, which should be from the end here. Let's find where that goes. I'm assuming this big header up here. So I should slow down. No. Okay, oh, sorry, I'm looking at a little header here. Oh. Okay. That header there. Actually, I didn't make anything for that header. Okay, so that's that one there. That was 1. Okay, 2 is right next to here. Have to be a contortionist for this kind of work. Right. Okay, so 4 for 1 is 2. Too fast for that. So 1, 2, 3, 4. 1, 2, 3, 4. So it's, yeah. So this will be. What am I doing? Oh yeah. That meter seriously pisses me off sometimes. You got time to think with it before it shuts off, goes to sleep for you. Right. 2. So, why did I write 5? It's actually 3. So 14, so it's 4 from the end here. So I'm going to do it this way. 4 from the end. Okay, let's find where it is. 4 from the end that way. And 4 is 3 from the end. I guess it has it, I guess, here. Nope. Surprised. Nope, number 1. Not number 1, it's this one here. Okay, now 5 is the one directly opposite from here. Still in screen. 5. So let's do that one. So that's 5. Right, it's terrible today. Okay, and 6 is number 4 up here. Second one there. 7. Oh wait, that'll be the one after that one. So 7. Oh wait. Oh yeah. 7. There's that one here. So that. So rows are circled. Maybe it'll be beneficial if I actually try and find VCC. So there's pin 1. Yeah, VCC pin. Is there going to be any VCC connections on here? No. Okay. How about ground? No VCC and no ground on here, which is odd. Now, out of curiosity, are these row connections duplicated? Yep. Yep. Okay. So the row is driven commonly, the logical input for the row is driven commonly throughout the entire thing, but the actual driving of the rows is done in groups of 3. Okay. So that leads me to think, now, how are the columns driven? So therefore that is strange. So that would make me think that the columns have to be individually driven. Unless I'm missing something here. And I've just noticed there's a silk screen saying bank 1, bank 2, bank 3 and bank 4. So my theory of them being separated into banks is somewhat right. Now, if they're being commonly driven, the rows through the here, then the columns need to be driven, and so that's 5 times 12, which can't bloody remember. 5 times 12. So that's 60 dots wide. So this is a 7 by 60 screen. Now, how do we select 60 columns? Well, we don't have enough pins for that, so therefore it must be somehow bank switched. Very interesting. Now, actually, there's one pin I did not check. The clock pulse. Now, are they common for all 3 banks or not? and that would be this pin here. Ah. They're not common. So therefore, we might be driving one bank at a time based on the clock pin. Right here. Let's double check I am right. Yeah, okay. So yeah, clock pin from one bank is not the same clock pin as another. Now I'm going to see if it'll, if it beeps onto any of these. Yep. Okay, so I would say CP1 because this is supposedly bank 1. Yeah. CP2. CP3. With that pin or this one? There's that one. CP4. Okay. Now, don't know where that pen goes. It does go somewhere. Oh, that's a badly soldered joint in there. Anyway. Let me just see, does this actually go anywhere? Yeah. This is just satisfying my own curiosity here. Doesn't go anywhere on there. Awfully odd. So we've got 1, 2, 3, 4, 5, 6, 7. We've got CP1, CP2, CP3, CP4. I would really like to know where that goes. But I guess it may come later. Right, let's see. I was having to think about maybe I should find where the power connections are. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9. Just so I've got the orientation. Alright, let's have a look. Let's look for VCC, which is pin 20. Which is that one. Okay. That's opposite here is ground. Let's have a look where ground is. So those are both ground by the looks of it. Are these both VCC? Yeah. So let's see. So there's plus V. Yes, it says. So yeah, so that goes to VCC, and this one says sub goes to ground. And obviously those go to ground and stuff, so I'm not even going to bother looking at that. Now these, I'm assuming this goes to ground. Yep. And the common goes to positive, so yeah. So there's our power signals. So we're getting there. We have the rows, we have the power. Now we just got to figure out the columns. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14 pins unaccounted for. Well, actually 15 if you want to include this one. Just straighten these out. Bugs me when there's crooked pins. So yeah. 15 pins. We've got 5 columns. And we got so out of curiosity, are these in some sort of ganged array? I've just thought these in groups are free, and they're separated by clocking them separately, and there's 15 pins available. 3 5's 15. So if I'm not mistaken, these inner pins should correspond to these, which should if I'm I guess that should correspond together with obviously the third one over there, or the fourth one, that and that. So let's try this. So obviously that is together, but that and that are not. But come on, no. Maybe because it's on the wrong side of the driver. So 3 4. Aha. Yeah. That's why. This is the other side of the driver. It was beeping a minute ago. Did I kill it? Or am I just not going to the right pin? Oh, I see. Yeah. Yeah. Okay, let me just count these chips again. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now I should be able to make now there's going to be 3 different sets of columns, if I'm not mistaken. Alright, let's try and find column 1, which is pin 13. This should be pin 13. So that should be column 1. So that's column 1 there. And to prove my theory, I'll find column 1 again. So that transmits to that. That's pin 13, column 1, yeah. So yeah, here we have the column drivers and the row drivers. So we have the that's not quite right. Okay. We'll do banks are free, whatever. So we have the row drivers. Okay. So that's the bus going in. Actually, it's 4 banks in there. So these are the drivers. These are the banks going in with the identical data, and these are the clocks. And then we have the column drivers. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right. And then basically they're all connected with an identical 15-bit bus. Was it 14? Anyway, 15-bit. Maybe that's what that extra pin here. Maybe that's bit 15. Let's put that to test, because I just realised I worked the numbers out wrong. Okay. Basically, it should. Yeah, there we go. Yeah, it does one of the bits. Okay, so yeah, that does one of the bits. There, so that is pin 13, so that's row 1. Oh, so row 1. Where did I go wrong? Okay. So that's the third row 1, because that's the third display. Was it the first? Yeah. Third display. So 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Yeah. Yeah. So that works out right. Okay. Now we've isolated the these pins. I thought I'd redo that, and I accidentally did that as well. But so ignore that. Anyway. So now we've isolated the inner pins of this connector. Now it's time to place them to these displays. Like, we did find that the this pin here was row 1 on display 3. So I don't think that's good. So row 1, 3 in the square. So I know it's the third display. And obviously 1, 2, 3. Repeat all the way down. So instead of working from the display upwards, I'm going to work from the connector backwards now. So we're going to go for the second pin along here. There we go. Oop. Right. Sure. Right. Let's try. Okay, let's see if we can trace this. There we go. That's that. So let's try. See what this goes to that. Let's go there, isn't it? Right. So 14, 13, 12. So hey, that don't make sense. Eight, 9, 10, 11, 12. Okay, that's odd. 1, 2, 3. Am I triggering some diode here? Yeah, I'm triggering a diode. That's what's going on. $14, 13, 12. I don't know. Doesn't make sense. No, it does make sense. I'm reading the numbers the wrong way around. That is not 12. That is 3. 3 is column 2. So that goes to that. So it's column 2, display 1. And this down there is actually column 1, display 3, not row. Okay, now I just gotta do the same thing with all the pins. Alright, goes to there, there. That is pin 4, which is column 3. C3. Jesus. What was that? Column 3, display 3. Oops. Okay, so 8, 9, 10. 10 is column 4, display 1. C4, 1. double check. It's definitely not connected, is it? No, okay. 1, 2, 3, 4, 5. I'm guessing it's over here. Yeah, it seems to alternate. To there, to there. Come on, where do you connect? Oh, right there. That's 13, so that's column 1, display 2. C1, display 2. Okay, this is 1, 2, 3, 4. I'm guessing over here. Nope. There we go. That's the 4th one across. Oh, there we go. 1, 2, 3, 8, 9, 10. This is 10. 4, 2. C4, 2. That is 3. So, column 2, display 2. So that's the 3rd one there. That's 13. Column 1, display 1. C1, 1. Slowly getting there. Another 7 pins to go. Okay, that goes to 1, 2, 3, 8, 9, 10. So 10, 4, 3, 4, C4. Okay, and that one is 1, 2, 3. C2, 3. C2, display 3. I'm assuming. Okay. I'm a little confused. One, 2, 3, 4, 5, 6, 7, 8, 9. So, Alright, let's do this again. 1, 2, 3, 4. So 4. 1, 2, 3, 4. Okay. 4 goes to there. Goes to there. 1, 2, 3, 4, 5, 6. And 6 is 5. So 5, 1. C5, 1. Okay. Okay, sorry about that, I had a phone call. Right. So 1, 2, 3, 4, 5, so the fifth one in. Okay. That's to there. Okay, so it's 1, 2, 3, 4. And 4 is column 3. 3, 1. So C3, 1. So 1, 2, 3, 4 this way. I reckon it's going to be over here somewhere. I was right. What a guess. That is that there. 1, 2, 3, 4, 5, 6. 6. So that's 5, 3. C5, 3. 2 more to go. Oh. 1, 2, 3, 4, 3, 3, 2. C3, 2, and one more. There. This is 6. 6, so it's 5, 2. C5 2. Okay, let's just have a look. So C1 1, C1 2, C1 3, C2 1, C2 2, C2 3. Let's C3, C3 1, C3 2, C3 3, C4 1, C4 2, C4 3, C5 1, C5 2, C5 3. Right. So now we have a pinout. All we have to do now is get a mock-up. Well, not a mock-up. Get a little board set up and power it up and give it a go. Okay, so I managed to get some code working for this display. You can't see it right now because the light's on. But I'm finding the Arduino is a little slow at the refreshing. So we have to trade off brightness against flickering. So we can make it super bright, but then you see the screen refreshing, which is not good. What I did is I set up a buffer, which is 12 word by 7, and that holds the data for the screen. Obviously we're wasting like a bit because it's only 15-bit in a 16-bit buffer, but well. Yeah, so yeah, basically the 15-bit by 7, 15-bit by 7, so it's 4 15-bit by 7 buffers, and then I'm making it right to the screen, one after the other. Actually, no, I'm making it right straight across, then one at a time. But rather than the rows in turn, I actually have it interleaved. I do 0, 0, 2, 4, 6, 1, 3, 5. That way the flickering is not as noticeable, but it's still there. So I'm going to turn the lights down. That's going to turn all the lights off, and you can see, you know, it's not the best. I don't know if you can see the flickering on the camera, but with my eyes, if I look away slightly, I will see a flickering, and there is a bit missing. There, it's a bit of a compromise. There's a bit missing here that's noticeable. These 3 displays, it's because these bottom 2 rows on these 3 displays are controlled by this chip. 2 of the gates inside this chip are actually blown, but thankfully I did reverse engineer the schematic. Mostly, there's a couple of bits I still need to work on, but there is a few unused gates actually on some of these other chips that I might actually just reroute just to get that working. And one other thing is there's this, so say the 10th dot in for each section doesn't appear to work. So you can't see it here because I leave it blank because there's space between the letters, but it doesn't appear to work, and I thought it was the Arduino doing that, but I'm not entirely sure. I think there might be something wrong with one of these chips and it's pulling that line low, but I'll have to investigate that at a later time. I just wanted to make sure I got this video out because between this section and the sections before, it's been a good 2 weeks or maybe even a month gap. So I thought I'd get this video finished for now and probably do an update when I get it repaired. But yeah, so the Arduino code for this will be available on my 39K website. Well, it should be available. If it's not, just check a couple of times after a few hours or whatever, and hopefully I will have it up there. But I'll try my best to get it up there. But anyway, so that's this display reverse engineered and working. And yeah. And thank you, Amir, for the display. And sorry I took a while to get this video done. I did get it reverse engineered pretty much the very first day he gave it me. I just haven't got around to finishing the software. Well, there we have it. That's the LED display reverse engineered. Hopefully that will give people tips on how to do reverse engineering with digital circuits. I know Dave Jones showed with analog circuits, which are a bit far more complex, and you have to understand basically the transistor logic and stuff, not logic, transistor theory that goes into it. With digital circuits, it is somewhat a bit more straightforward. Basically, you get the data sheets of the equipment, the data sheets of the chips used, and basically just use a truth table, and you can work out exactly what's going on. And sometimes once you get all the inputs mapped, you'd use a bit of trial and error and logic to work out the correct sequence of things. Like I found the 15-bit that you insert, it wasn't all in order logically as to what was displayed physically on the display. It was somewhat, each section of 5 was reversed and flipped around. So yeah, it took me a few minutes to figure that out, and just made a few adjustments in the way that the line is written, and it now works. It matches the variable, and you'll see that if you look at the code. I plan probably to port this over to a PIC and run it faster, because I don't think the Arduino was fast enough to make it useful at all. I think that's running what, 16 megahertz or something. Anyway, it was it was just something I had at hand. But I could put a PIC 18 K, no, a PIC 18F 14K80 or something, running at 18 megahertz or some 60 megahertz or some bloody crap like that. Get one of them on it, and that should keep up with the refresh, no problem. Yeah. But anyway, yeah. So that's that for now, and hope you've enjoyed the video, and thanks very much, and I'll see you next time. Goodbye.